Objectives of the fault analysis. So in this case, the major objective of the fault analysis is designing of the protective gears, or we call them also switch gears. I have already told you the major objective of the fault analysis is designing objective of the fault analysis is designing of protective gears or switch. Designing of protective gear or switch gear. This is the main objective of the power system. This is the main objective of the fault analysis. That why we go for the fault analysis. So what is the major objective? Major objective of fault analysis: designing a protective gear or a switch gear. So what switch gear means? Relay. And what basically means switch gear? Switch gear means relay and circuit breakers. I told you yesterday also this one. This is the meaning of switch gear. That means consists of relays or circuit breakers. This is the main objective. Now let me draw a small scheme. This is a small scheme. Okay, then we have box. After that, we have a transmission line, and then transmission line is having two bus bars. We have a bus bar here and we have a bus bar here. So, and this is the generator. This is relay plus circuit breaker. We call it, I will write it like relay plus circuit breaker. And this is from here we start this is our protective from here to here is our protective zone. And this is your load. So this is a small schematic there showing a generator plus relay and circuit breaker with two bus bars, and then we have a protective zone up to the load. Now let's see what should be the relay rating selection. What should be the relay rating selection? Let's see how we can choose the rating of the relay. First, I will clear this again yesterday. This is a schematic. What is the scheme of protection we have? This subject in detail you will study in 7th semester. Scheme of protective gear. So scheme is like this. Then we have a relay followed by the circuit breaker. So this is your pickup current. I will talk about this current. This is relay, and this is trip signal will be issued by in case of abnormality, trip signal will be issued by the relay. Trip signal, this is circuit breaker, and then isolation of the faulty part will occur. Okay, so what's a circuit breaker? Circuit breaker, it breaks the circuit, you know already, in a sense that it will isolate the healthy section of the power system from the unhealthy section. Why? So that the continuity of the supply to the consumers is not disrupted. I will repeat it again. It breaks the circuit. So main purpose of the circuit breaker is it breaks the circuit, number one. Then it breaks the circuit in a sense that it isolates healthy section of the power system healthy section of the power system from the unhealthy section from the unhealthy section, so that continuity of supply the electrical supply to the consumers is not disrupted. So supply is not disrupted. So it's very clearly it will break the circuit, and how it will break, it will just isolate the healthy section from the unhealthy section, so that there is no disruption in the electrical supply to various consumers which will be there. Next is relay. I have already told what is the relay. Relay, it gives intimation or signal to the circuit breaker. It gives intimation or signal to the circuit breaker. Okay. And you should always know that majority of the faults which occur in the power system are short circuit faults in comparison to the open circuit fault I told you. So we know that majority of faults in power system are short circuit faults in comparison to what? In comparison to open circuit faults. So this is, you should always know. That means we have symmetrical or unsymmetrical faults. They will more occur in the power system as compared to the open circuit. One conductor fault, one conductor open fault, two conductor open fault. They are less, which we have seen yesterday in the category of the faults. Now, in case of, if we talk about more about the short circuit, in case of short circuit faults, what will happen? You know, short circuit voltage will be zero. In case of short circuit faults, voltage at a particular bus will become zero. And when the voltage will become zero, then subsequently the current will increase. Therefore, input to the above protective scheme which we have drawn here, this is the protective scheme we have drawn. Input to this protective scheme is nothing but current. So what we are telling, in case of short circuit fault, voltage at particular bus, short circuit fault, what will happen? Voltage at particular bus becomes zero. That you know already. Short circuit means voltage is zero. Particular bus becomes, it will become zero. The voltage at particular bus is going to become zero, and subsequently, with as a result of this, current will increase, and subsequently the current will increase. This is for sure. When the voltage is zero, the current is going to increase. Therefore, the input to the above protective scheme is what? It is basically current, because voltage has become zero. Protective scheme is current. Now, we were talking about the ratings now. You should remember that IP. It's very clear that in case of short circuit fault, voltage at a particular bus is going to become zero. So that is going to increase the current. So whatever is input going to the scheme, that will be only current. So there will be no voltage at all. So IP, we will talk about. IP is pickup current. Pickup current, it's a pickup current which would be picked up by the protective scheme. That is, if we talk about more precisely, then it will be the relay. And I is the normal operating current. IP is a pickup current. I is the normal operating current. Okay, so IP is the normal operating current. So what should happen during the normal conditions? That's a normal operating current, should be always less than the pickup current. So we will call it a normal operating condition. I'll again repeat, IP is a pickup current and I is a normal operating current. So normal operating current has to be always less as compared to the pickup current. So when this happens, so there'll be no trip signal, because we have to issue a trip signal to the circuit breaker in case of the abnormality. But in this case, if everything is normal, operating current is less than the pickup current, then we don't have to worry. So no trip signal will be issued to the relay. But if it is vice versa, that IP is greater than the normal operating current, then what will happen? This will be treated as the abnormal operating conditions. These are not the normal operating conditions. So these are the abnormal operating conditions, and we can say this is fault. Fault has occurred in the power system. So in this case, what is going to happen? Trip signal will be activated. Now here, the trip signal will be activated and will be issued to the circuit breaker will then what do? So what is going to happen? Hello, Assalamu alaikum, sir. Sir, class bă caro pat phone. हाँ सर बो वनो ना तो आकर बहुत क्लास पे पर्नावान पे मे डिस्टर्ब मैंने इनको टाइम रखा है बह क्या कर मैं अपने मे तूता डिस्टर्ब पर यहाँ से डिरेल होके मैं फिर इनको ऑन करता रहता हूँ वहां से रिकॉर्डिंग भी मैंने रखी चलो वह करो वह क्या करो चलो क्या पर बेटा आप ध्यान रखो ना फिर वी हैव टू लॉट्स ऑफ थिंग्स आर हैपनिंग हियर तो वैसे भी okay, what will happen now? So in this case, the trip signal will be activated. So if trip signal is issued, what's the problem? If the Now what will happen if the trip signal is issued? So when we are talking about this, we are talking about this abnormal condition when the pickup current is greater than the normal operating current. So what will happen? Trip signal will be issued. That means circuit breaker will issue a trip signal to the circuit breaker, sorry, to the relay, and that will issue it to the circuit breaker. Then what will happen? Then circuit breaker will isolate just a second. Okay, fine. What will happen? If the trip signal will be issued, because in abnormal conditions are there, so trip signal will be issued, then circuit breaker will isolate the faulty section of the power system. So circuit breaker is going to isolate this. Okay. Now, selection of relay ratings. That's again we'll be talking here. We're not talking about the selection of relay ratings. Selection of relay ratings. Let's see this, how we are going to do this. Now, you should always remember when we are selecting the ratings for the relay, then it is based on the least severe fault. So, ratings are for a relay, ratings are based on what? On least severe fault. So ratings are based on the least severe fault. That is least severe fault. We will talk about it. That's a LG fault, line to ground fault. Why? Only one line and a ground are involved in this case. So whatever the ratings will be chosen, that will be chosen on the relay, because a minimum current is required, so that abnormal type of current is required to give a trips to issue a trip signal. So that rating has to be based on the least severe fault. So in case LG fault, in the case of LG fault, it's a least severe fault. What will happen? The magnitude of the fault current will be less as compared to the magnitude of the fault current will be less. That will be less as compared to what? As compared to, we know that, we'll see that also, as compared to triple L fault, because all the three lines will be involved. All the three lines, there will be short circuit for the same circuit condition. If the circuit conditions are same for the same circuit conditions, if we are having the same circuitry, then what is going to happen? In case when we talk about the LG fault, the magnitude of the line to ground fault current will be very less as compared to the LL fault. So we will be talking about the least severe fault, that is LG fault. So whatever the current flows through through that circuitry, that current will be required to issue a trip signal. So that's very important. So we require least current here, not maximum current, because maximum current we will be ignoring the least severe fault. So we have to take all the faults into the consideration. That's why we are talking about the least severe faults, and the magnitude of that fault current is going to be less. So next is, okay, next we will talking about, now switch gears are designed for what? They're designed for protection against faults. So switch gears are designed for protection against. You should always remember, if we have a scheme, protective scheme, those switch gears will be designed for the protection against the fault. They are not designed against the overload. Not against overloading. We have not any design sort for we will, okay, overloading will happen, then we will do something. No. If an abnormal condition will happen, that's what the switchgear will be there for. So when we talk, we should know I overloading, that means current which will be flowing through an overloading condition should be less than I pickup current, which should be further less than I fault. That means the fault current will be the maximum. So this is the condition we have to see, and that fault current will be during the, because we are choosing on the basis of the least severe fault. Least severe fault is which one? That is line to ground fault. So I loading should be less than I pickup current, and which should be further less than fault current, which will occur during a least severe fault. Now second, we'll talk about the circuit breaker rating. This is the relay. So relay based, what you have to remember, ratings, somebody will ask, you have to, relay ratings will be on the basis of the least severe fault, and that's least severe fault we already know is a LG fault, because why? The magnitude of the current is less as compared to the other faults. Now circuit breaker rating selection, how we do it? Okay, what we do in this case, circuit breaker rating is an MVA. You should always remember, circuit breaker rating is in what? Everybody knows that MVA, that's in megavolt amperes. Then circuit breaker rating is conversely contradictory what we are using in case of relay. Circuit breaker rating is based on the most severe fault, because we have to isolate. Circuit breaker rating is based on most severe fault. That is either in case of the short circuit fault, it is triple L fault or triple L to G fault. Okay. What will happen? The current for the various, the current for the various faults will be different. So will be the power. Hence, circuit breaker should be able to sustain a maximum MVA during LL or double LG fault. Hence, this is the reason that the rating is based on the most severe faults. So when circuit breaker rating should be able to sustain, circuit breaker rate it should be able to sustain a maximum MVA during the triple line or a triple line to ground fault. So I will write the reason. The reason for selection is the current for various faults will be different. That we know already. We'll see that in coming lectures. So will be the power in terms of MVA now. Okay. Hence, what should happen? Hence, circuit breaker should be able to sustain what? should be able to sustain maximum MVA during most severe faults during occurrence of triple L or triple LG faults. Okay, so that's why hence the rating is based on these. This is the reason that hence rating is based on these faults. So it should be very clear if somebody will ask you about the relay. It's based on the least severe fault, while as the circuit breaker is on the basis of the most severe fault, that is triple L fault or triple LG fault, because it should be able to sustain the maximum power. Power will be indifferent. So this was about the relays and the circuit breakers. Very simple and objectives of fault analysis. These are our objectives, and this is the protective scheme we will be having. So next topic is assumptions made in fault analysis. What are the assumptions we will make? How we are analyzing the fault. Then while analyzing the fault, what are the assumptions we already take into the consideration? Let us see all those assumptions. Assumptions made in fault analysis. So let's see what are the assumptions. Okay. First assumption which we consider is transmission lines, we already know, are represented using series reactance only. So series resistance of the transmission line is ignored, and also shunt branches are also ignored. We have discussed this earlier also, and same will be continued. So transmission lines are represented using series reactance only. So during fault conditions, what we have to represent transmission line? Series reactance only. And then the series resistance of transmission line is ignored because the value is very less as compared to the reactance is ignored, and shunt branches are also reasons I have given earlier in the earlier lectures, and shunt branches are also ignored. So first and the foremost point, we have already studied this earlier also. Transmission lines are represented by what? Series reactance only, resistance is ignored. Reason is resistance value is very less as compared to the reactance, and shunt branches we also ignore because current flowing through them will be very low. Transformers are represented using leakage reactance only. Are represented using leakage reactance only. And then magnetizing branch of transformers are ignored. Magnetizing branch of the transformers are ignored. Okay. And also phase shift due to star delta configuration is also ignored. Due to star delta configuration. What is the phase shift? It's normally 30-degree phase shift. Star delta configuration, which is normally 30-degree phase shift, is also ignored. So next is transformer. We know already represented by the leakage reactances only. And then we don't consider the magnetizing branches also. We have given the reason for that also. And then phase shift due to this star delta configuration is also ignored in this case. Next is synchronous machines are represented by constant induced EMF in series, that we have also seen. Synchronous machines are represented by constant induced EMF and series reactance. That we have already seen. So synchronous machines, generator, motor can be represented by voltage source and a series reactance. Then leakage resistance of the synchronous machines are ignored. Leakage resistance, because that's also very less. Leakage resistance of synchronous machines is also ignored. We don't consider that because value is very less. That obvious reasons are there. And then saliency of the machines is also ignored. It's also ignored. So saliency means what? Saliency means cylindrical rotor. If we talk about the saliency, that means you have studied in the machines. Cylindrical rotor. Cylindrical rotor means the saliency. That is ignored in this case. We don't consider that saliency. Next is static loads. As we have seen, static loads are not taken into consideration in fault analysis. All the static loads, we don't consider them. All the static loads are not taken into consideration during consideration in fault analysis. We don't consider the static loads. So all the static loads are not considered. We don't consider them in while we are milling. Any kind of pre-fault loading is in. We don't worry about the pre-fault conditions also. In the system, any kind of pre-fault loading in the system is ignored also. Okay. So next is three-fault analysis, three-phase fault analysis. So this was very simple fault analysis. What are the various assumptions we make, and that those assumptions you already know. I have repeated here, but you already know these assumptions, what we'll be doing. So next is three-phase fault analysis we'll be making now. Three-phase fault analysis. Okay. Okay, three-phase fault analysis. In order to do that, let us go to the next page only, because we have to draw a diagram. So three-phase fault analysis, how we do? We'll write the heading here again. Sorry. Three-phase fault analysis. Okay. I'll draw the diagram first and for the okay, this we are drawing. What we are trying, three-phase generator will be connected to three-phase motor via the transmission line, so that supply will be provided to the motor. That's what we'll draw the diagram. Then we'll explain it. Okay, so we have motor here. Reactance of the motor, voltage of the motor. Just a second. Okay, then what we have the space. I'm making the connections like this. Okay, so let's make first this one clear. So this will be phase A of the generator. That will be phase B of the generator. That will be phase, okay, C of the generator windings. Okay, similarly we will have here for the motor, because motor will be connected via transmission line. I have already told. I will give that complete details. Okay, bear with me. You can draw the diagram later. But okay. Okay, so this is This is first is generator, this is motor. Okay. So this also is a reactance of the transmission line. Reactance of the transmission line. Reactance of the transmission line. Okay, let's say we'll consider a fault here at this location. So let's consider a three-phase fault. Okay. So this will be connect phase A, B, and C. A is connected to, we'll draw the connections first. Okay. So look into connections. They're very simple. Each phase is connected. Okay. So this will be connected. Okay. So let us draw the reactance of this one. We consider this like this. This is reactance. Sorry. Okay. So this is your generator. Now we'll be drawing it. This is phase B of the generator, phase C, each having reactance. So this is A, B, and C. The respective currents will be respective currents will be IA, IB, and IC. Then this is XL, XL, XL. Let us say this is motor. So we will say this is E dash, EB dash, EC dash, just for the identification sort. Okay. So this is a fault. We have considered three-phase fault, and we'll be writing it as F here. So this is your ZF, fault impedance ZF, fault impedance ZF. So we will have currents flowing through them. IFA. Okay. So again, this is your A, B, and C. Okay. So this is your arrangement that we are connecting. What basically we are doing here? Basically we are connecting a generator to three-phase generator to a three-phase motor via a transmission line. Then we are considering a fault which has occurred at the point F. This is a three-phase fault. Sorry, this has to be a jump connection here. So you can see Generator is connected to A phase, B is connected to B, C is connected to C, and transmission, each has a transmission line reactance. You can very clearly see. Then fault occurs. So fault occurs here at point F, then fault occurs like this. It's connected to ground, is connected to phase C. This is connected to, again, to both the phases, and this is connected to C phase. So it's a three-phase fault where all the three lines are involved. So now what are our, as in, this is the circuit which will be at the time of the three-phase fault. When the circuit will occur, the fault will be like this. Now what we are doing, basically a three-phase generator is for making analysis of the three-phase fault. Three-phase generator is connected to three-phase motor that you can see via what? Three-phase motor via transmission line, and it will provide what? Providing supply to motor. This is a normal three-phase generator is supplying electrical supply to motor, and motor is running as usual. Now, at pre-fault conditions, system is operating in balance condition. So pre-fault condition, there was no fault at all. At pre-fault conditions, system is operating in balance conditions. Okay, so system is operating in balance. Now what will happen? Now this is the normal operation of the power system. Nothing is happening. Three-phase generator is connected to three-phase motor, and pre-fault conditions are there, and we don't have any sort of abnormality in the power system. But let's say suddenly a balanced three-phase load is connected. Balance, what we'll do now, we'll do three-phase. Suddenly a balanced three-phase load is connected at what? At point F. So you can see at point F, in order to show the fault analysis, in order to analyze this fault, we have shown a fault will occur at point F. That's a three-phase, all the three-phase fault. Okay, so what will happen in this case? The three-phase load, for the sake of analysis, this is the three-phase load is termed as fault. Three-phase load will be termed as fault when, so at that time when value of ZF will become what? Very low, because fault current will be very high, value of ZF is low, and it's almost equal to, in case of short circuit, we always say that ZF is equal to 0. Now if ZF is equal to 0, then what will happen? Then fault current is termed as, fault current will be very high, then fault is termed as, which type of fault it is? Solid fault, or sorry, it's termed as solid fault, or this is an ideal fault. So impedance will be low, current will be very high. The name of the fault given that time is a solid fault. The certain connection of impedance introduces what? Now, when you connect this impedance, fault impedance, with the three phases as shown in the figure, then certain connection of this will introduce a transient in the system. I hope you know transient. Transient is a very short time at which the value will abnormally go down in this case. So from any value to it will go zero. So, sorry, the sudden condition of, sorry, the sudden connection of this of the impedance ZF will do what? It introduces transient in the circuit. It will introduce a transient in the circuit. Sorry, circuit, or better to write system. To introduce transient in the system. And the fault current, as I already know, will consist of, it will be very high. And now fault current, that we will study in further lectures, fault current. Now when the transient will be introduced, so fault current will be having two components. Fault current consists of two parts. What are those parts? The fault current will consist of two parts. It will have AC component and DC components. Okay, only AC component will be considered, and DC component is computed using empirical. We don't consider DC component. That will be computed using a particular formula. So once we are analyzing the fault, only the AC component or the fault analysis, what we will do, once the impedance introduces transient, once the transient is introduced, as we have seen, there is a transient and then there is a steady state part. So it will, the current will have two parts, AC component and DC component. Only AC component will be considered. Here only AC component will be considered, and DC component we compute using empirical formula. DC component is computed using empirical formula. That means we have tried something and we have reached a particular consensus or result. That formula is called empirical formula. So very simple, that we will have two parts of the current, AC and DC. AC will be considered, DC will not be considered, and we will have a particular formula for that after a certain trials, after certain experiments. Okay. Now we'll end this, I think. Yeah. So, okay, we'll continue with the next lecture because time is. Now, post-fault analysis, how we will do? I will tell you something about that. Post-fault analysis will be done because the conditions, pre-fault conditions were also balanced and the post-fault conditions are also balanced, because we are introducing three phases in the system as a fault. So post-fault conditions also balanced in nature. So hence we can directly go for the per phase analysis. That means we will analyze a particular phase and the results will be extended to all other phases. So that is very easy, and we can see that in the next time, and we will finish this part. Okay, that's all for today's lecture, and we'll be continuing with this lecture maybe day after tomorrow or tomorrow. Mumin.